Hello, welcome to Algebra 2 Common Core. Today we're going to review systems of equations from algebra and then challenge ourselves by moving on to systems of three equations with three variables. So we're going to go over two different methods for solving systems of equations that you learned back in algebra. The first method is called the method of elimination. By the method of elimination, we look at our two equations. This set of two equations each have an x and a y variable. We're going to look for a way to eliminate one of the variables from the equations. So one way of doing this is to take our second equation and multiply the whole thing by -2. We're choosing that number -2 so that when we distribute the -2, the coefficient in front of the y will be -2. We'll then be able to add our equations together, giving us a 0 in the y column. So our first equation is going to remain 3x plus 2y equals -9. The second equation, when we distribute the -2, becomes -4x minus 2y equals 14. Now we can go ahead and add those two equations together, thus eliminating the y. That's why we call it the method of elimination. So the y terms cancel. That gives us a -x is equal to a +5. Dividing both sides of the equation by -1, we see that the x answer is equal to -5. Now, of course, we're not done because we also need to know what the answer for y is. Pick one of the original equations, so I can pick either of these equations. I think I might pick the second equation because it's just got a single y in it. So I'm going to take the second equation, 2x plus y equals -7. I'm going to replace the x with my answer for x, -5. And I'm going to multiply, so I have -10 plus y is equal to -7. And when I add 10 to both sides of the equation, I get y is equal to 3. So my solution for this system of equations is the ordered pair x is -5, y is equal to 3. This ordered pair would be the point where the two linear functions would intersect on a graph. For the second set here, x minus 3y equals 7 and 2x plus 5y equals 3, I want to use the method of substitution this time. So using the method of substitution, I'm going to pick one of the equations that I can solve for one of the variables. The one that I'm going to pick this time is the first equation because I see that it has an x that would be easy to get by itself. So I'm going to rewrite that first equation by adding 3y to both sides of the equation. So that gives me x is equal to 7 plus 3y. Now this is called the method of substitution because I'm going to take that answer for x, 7 plus 3y, and I'm going to substitute it into the other equation where I see an x. So I'm going to say 2 times 7 plus 3y plus 5y is equal to 3. Now we have an equation that just has one variable, the variable y. So we're going to distribute the 2, and we have 14 plus 6y plus 5y equals 3. Adding together like terms, I now have 11y. I still have the 14 that's being added to it. We want to get the y by itself, so we're going to subtract 14 from both sides of the equation. That gives us 11y is equal to -11. Now when I divide both sides of the equation by 11, I now have the solution for y. Y is equal to -1. Again, that's not our final answer. I need to know what my x answer is as well. So I'm going to take that equation that I wrote where x was equal to 7 plus 3y, and if x has to equal 7 plus 3y, I'm going to replace the y with a negative 1, so x is equal to 7 plus 3 times negative 1, so therefore x is equal to 7 minus 3, which is 4. My solution this time, make sure that you always put your x coordinate first, so x is 4, y is negative 1. Now, of course, we could check either of those solutions. So, for example, in this case, for negative 1, we could check by substituting 4 in for x into this original equation and negative 1 in for y. 4 minus 3 times negative 1 does equal 7, so that's correct. That solution has to work in both equations, so if we substitute it into the second equation, 2 times 4 is 8, 5 times negative 1 is negative 5, 8 minus 5 does equal 3. In Algebra 2, we're going to have more of a challenge because we are going to solve 3 equations, a system that has 3 equations, so it has to have 3 variables, this time x, y, and z. Now we're going to use the same methods that we saw in the previous easier examples. So I'm going to look at this system and I'm going to say, I want to be able to eliminate one variable from this system. When I look at my variables, in this example, the easiest one to eliminate looks like it's going to be z because I've got a positive z and 2 negative z's. I'm going to deal with just 2 equations at a time. So to begin with, I'm going to start with the first 2 equations. 2x plus y plus z equals 15. And 6x minus 3y minus z is equal to 35. I'm going to do that method of elimination, so I'm going to add those 2 equations together. When I do that, I'm now going to have 8x minus 2y. I see that the z's, a positive z and a negative z, will be eliminated, and we'll have equals 50. Now, to make my work a little bit easier, I notice that all 3 of these terms can be divided by 2. So as long as I do the same thing to the left side and the right side of the equation, I'll still have an equivalent equation. So I'm going to divide both sides by 2. So I've got 4x minus y equals 25. And that's as far as I can go so far with those 2 equations, combining them. Now I'm going to go back to my original set of equations and pick a pair, other than the first 2, that I can also eliminate the same variable z from. So I see that I could use the first and the third equation this time. So reusing the first one, that's okay, we can reuse. 2x plus y plus z is equal to 15. And the third one, negative 4x plus 4y minus z is equal to negative 14. So again, I'm going to combine those 2 equations because I want to eliminate the same variable that I did in the first case. I'm going to combine these 2 and rewrite it in red. 2x minus 4x is negative 2x. Positive y and positive 4y is plus 5y. The z's are eliminated because they cancel, and this is going to be equal to the number 1. So now I have the new blue equation and I have the red equation. So I've simplified my process because I've eliminated the z from the whole system, and I can now go back to what I did on the previous examples and put these 2 together. The easiest way to combine the blue equation and the red equation to eliminate one variable is probably to look at my 4x in this equation and negative 2x in this equation. If I take my red equation and multiply the whole thing by 2, I'll see that the x's are going to cancel. So I'm going to rewrite my new red equation down here after I distribute a 2 through the whole equation. So 2 times negative 2x is negative 4x. 2 times 5y gives me a positive 10y. And 2 multiplied by 1 is going to give me a positive 2. Now I've got two equations that can also be combined. They're in terms of x's and y's. In this case, I'm going to eliminate the x's because they add together and cancel. Adding together the y's, I've got 9y is equal to 27. So therefore, y is equal to 3. So that's my first part of my solution for this system. I need to find the answers for the other two variables so I can pick one of the equations that has an x and a y in it to solve for x. Let's go back to the red equation, the simplified one, and let's substitute into that equation my value for y. So negative 2x plus 5 times the y answer that I just found, 3, has to equal 1. Negative 2x plus 15 equals 1. If I subtract 15 from both sides, I have negative 2x is equal to negative 14. So x is equal to 7. So here's another solution, another part of our solution for this system. Let's keep going. Now we've got to go ahead and find the z. To find z, we're going to have to go back to one of our 3 original equations because they're the ones that have the z in it. I'm going to just use the first one, so 2x plus y plus z is equal to 15. I'm going to substitute 7 for x. I'm going to substitute 3 for y, and that will allow me to solve for the z. 2 times 7 is 14, plus 3 plus z equals 15. So 17 plus z is equal to 15, which tells me that my final answer for z is negative 2. When we write our final solution, we write it in the order of x, then y, then z. So my x answer is 7, y answer is 3, z answer is negative 2. So there is my final solution. Again, I can go back and substitute all 3 of those values in one of my original equations. In fact, you should substitute them into all 3 of the original to make sure that it works. Let's try exercise number 3, where again we are going to try to solve a system that has 3 equations with 3 variables. In this case, I looked at all 3 equations and I decided that the variable y was going to be the easiest one to eliminate this time. When I look at the first and the last equation, I see that they have a positive y and a negative y. So it would be easy to eliminate the y's when I add those 2 equations together. So you'll notice that I wrote the first equation and the last equation, and I combined like terms, eliminating the positive and negative y, to get the following equation. 9x minus 10z is equal to negative 25. Now let's pick 2 different equations that I'm going to put together. This time I'm going to pick the second and the third equation. I still need to eliminate the same variable, so I need to eliminate the y. I picked the second and the third because I saw that in the second equation the y was positive, in the third the y was negative. So I'm going to keep the second equation exactly as given to me in the problem. Negative 2x plus 4y plus 2z is equal to 38. In the last equation, I'm going to go ahead and I'm going to multiply the whole equation by a positive 4. That's going to give me a negative 4y that'll eliminate the y's in my equation. So I'll have 20x minus 4y minus 28z is equal to negative 76. Had to do that one on the calculator. Go ahead and add together your like terms here. So we're going to get 18x. Again, the y's will cancel. So it'll be a minus 26z is equal to negative 38. Again, I see that that equation can be divided by 2, so I'm going to simplify it by saying 9x minus 13z is equal to negative 19. And that makes it a lot easier. Now, if I take that whole equation and I negate it, I'll be able to add it to this previous equation. So I'm going to write negative 9x plus 13z is equal to positive 19. So I've just taken this result and negated the whole thing so that I can add it together with the first result and eliminate the x's. So I now have 3z is equal to negative 6. Dividing both sides by 3, z is equal to negative 2. There's one part of the 3 parts to my solution. I now need to choose one of the equations that has an x and a z in it, so either this one or this one. It doesn't matter which one you pick, either one will work. So I'm going to go back to the one that says 9x minus 10z equals negative 25. So substituting my solution for z, 9x minus 10 times negative 2 equals negative 25. 9x, negative 10 times negative 2 is plus 20 equals negative 25. If I subtract 20 from both sides of the equation, I have 9x equals negative 45, so x is equal to negative 5. So there is my answer for x. Now I pick one of the original equations, and I'm going to go right back to the first equation that we had. 4x plus y minus 3z equals negative 6. Using any of the original 3 equations, I can now solve for my last variable y. So 4 times negative 5 plus y minus 3 times negative 2 is equal to negative 6. Negative 20 plus y plus 6 equals negative 6. Combining like terms, I have negative 14 plus y equals negative 6. So my answer for y, when I add negative 14 to both sides, is that y is equal to 8. So once again, when we want to write down our final solution, we would write that in the order of x-coordinate negative 5, y-coordinate 8, z-coordinate negative 2. So it's always an ordered triple that I'm going to have as my solution. Look over this solution. Notice that there are very often many ways that you can solve these equations. For example, I'm noticing that I could have probably also taken my second equation originally and divided everything by 2, and that may have made the numbers a little bit smaller in my problem. As long as I do the same thing to both sides of the equation, it will solve the original. I can even use my calculator to check this by storing negative 5 for x, 8 for y, and negative 2 for z in my calculator, and then typing these equations in using the variables x, y, and z. You'll have to use the alpha key if you're going to try that on your calculator. Let's move ahead to exercise number 4. Looking at exercise number 4, I noticed that it might be a good idea to eliminate my x's this time from all of the equations. I'm going to go ahead and do my work, so pause the video. You try it on your own. Try to eliminate the x's first of all, and see if you can solve the problem by doing that. Come back and check your solution with mine. You may not follow exactly the same steps, but if you've gotten the right answer, that's perfectly acceptable. Hi, welcome back. Did you get the solution? -1, -3, 7? Take a look at my work, and again you'll notice that I combined the first equation with the third equation, and when I did that, it worked out really nicely because the x's and the y's both canceled. That gave me a solution right away for z. So I could take that answer for z and I could substitute it in any of my original equations. I put it into the first equation first of all, simplified it to get x and y as an equation. Then I substituted 7 into the second equation, this one right here. Again, I simplified that one. I then had to work with the two equations that remained, and I had to multiply this one by a 5 so that in these two equations the 5y's would cancel. That led me to the solution that x was equal to -1. I then took that answer and substituted it into this equation to find my answer for y, -3. These can get very complicated, and if you make a mistake, whether it be a sign mistake or an addition mistake, it kind of throws off the whole problem. So when you make a mistake, you've got to go back all the way through your work. We'll be practicing some more with these during class time.